In our attempt to model this situation and to think about what's going on, we see that the thing that makes the temperature change is not the temperature itself, but the difference between the temperature and the room temperature. If I let T stand for the temperature of the object, TR for the temperature of the room, then I can define this TD, which doesn't stand for touchdown, it stands for temperature difference, the essential difference between the temperature and the room temperature. Since the temperature of the object approaches the temperature of the room, then we see that we're going to have a graph that's asymptotic to the t-axis. At any point, or in the neighborhood of any point in this graph, we're going to be able to calculate an average rate. So we've taken 2 points, point 1 and point 2, and we've calculated perhaps an average rate 1. Now we haven't actually calculated it, we're just depicting it, but that average rate is going to be represented by the rise over the run of this little triangle. I haven't drawn the triangle very well, the run should be more horizontal, but the camera perspective is throwing things off a little bit here too. So what we have at this point is some temperature difference, which we'll call T sub D sub 1, temperature difference 1, and an average rate that we'll call average rate 1. Over here we have a smaller temperature difference, T sub D2, and a smaller average rate. Obviously we have more run for the rise, a smaller rise for the same run, whatever you want to say. It's obvious that the slope here is going to have a smaller magnitude than the slope here. Okay, these slopes are negative, so this one's actually less than this, but it's smaller in the sense that the temperature is changing less quickly. The absolute value or magnitude of the slope is smaller here than it is here. Okay, so again, the point that we don't want to lose is that when we have a larger temperature difference, we have a larger magnitude of the average rate. And a smaller temperature difference means the magnitude of the average rate is smaller. We could hypothesize that the rate of temperature differences, temperature difference 2 divided by temperature difference 1, is maybe equal to the average rate 2 over the average rate 1. This would be the case if the temperature difference and average rate were directly proportional. If the average rate is directly proportional to temperature difference, then this is exactly the ratio behavior that we'd expect, as we've seen abundantly in our study of proportionality. Now, that's not necessarily true. Maybe we have a square around this, or maybe it's the 1/2 power, or maybe it's even inversely proportional or something, but we'll hypothesize a first power so that we might say, if this is the case, that the average rate is proportional to temperature difference, so that the rate is some constant times a temperature difference. Of course, that's how we express a direct proportionality. It turns out that for exponential functions, this is the case. And any time this is the case, we have an exponential function, so that this rate equals constant times whatever quantity we're graphing in the y direction, whatever quantity is being represented. That is, t is the quantity whose rate we're measuring. If the rate at which t changes is proportional to t, then we're going to have an exponential function. And it turns out that this is exactly what we seem to have for most objects as they approach room temperature.